did anyone read that? Phil has. What about Cauchy's integral? Do you see that to indicate the style of integral, it's quite common for Cauchy's integral to have this, right? For the Riemann integral to have that. Lebesgue integral to have that.
If it's not written, it's going to be the
Riemann. Yeah. Riemann Stieltjes. So you put a nice flowery scripty abbreviation out front to indicate whose integral definition you're appealing to when you construct. Let's talk for a minute about, before we talk about Cauchy's integral, what exactly is it? What's the fundamental theorem of calculus and what did Newton and Leibniz really do? You saw Fermat was able to get areas under power curves. What was the big breakthrough in Newton and Leibniz? They presented a method that was much more general. Everything up to that point was ad hoc, a very special case. So the breakthrough was general cases. Now you may not always be able to do the integral in some closed form. It may be a very obscure one. It's very difficult to do. It's easy to write down integrals that you can't do. Here's one from 2 to 3 dx over ln x. Nobody has yet successfully done that in closed form. There's a theorem that somebody ought to dig up from the 1840s. It gives sufficient conditions, I think, for an integral to have a closed form expression in terms of elementary functions. And I can't quote you the theorem at the moment, but it allows you to, I'll investigate this, it allows you to make a decision according to some basic criteria, rather than general criteria, whether this can even be done. At any rate, so what is it? Why do you need all these integrals? Why is there a proliferation of integrals? What's the improvement? What are they trying to do? I mean, once you have the Cauchy integral, why not stop there? What do you need? What do you want? Well, it's an extension of what Newton and Leibniz were doing from what the ancients were doing, increasing generality. A fundamental theorem of calculus is this. It's a method of recovering a function given its derivative. You would like to remove as many restrictions on the derivative as possible and still be able to carry out the construction of the function whose rate of change is given. The Riemann integral is great, but you need the function to be continuous. That's a pretty strong property. Right? Continuity is a pretty heavy-duty property. So it was Lebesgue himself, around the turn of the last century, who proved that a necessary sufficient condition for the Riemann integral to exist was continuity of the function. Mathematicians like to generalize, a stronger theorem is one that has a tighter conclusion, a stronger conclusion, and a weaker premise, or premises, right? So you'd like to get rid of some of the statements like has to be continuous, right? You'd like to get rid of stuff like that. So the search for ever better definitions of integral has that motivation. Weaken the assumptions, strengthen the conclusion. You can state it in terms of the class of functions that have integrals according to the various definitions. Functions that are Riemann integrable are Cauchy or Lebesgue integral, but not vice versa. There's, if you draw the Venn diagram, these are the Riemann integrable functions, and then the Lebesgue ones are ever so slightly bigger. And then the Kurzweil end stop ones are even a little bit bigger than that. And I thought we'd spend maybe next week, if we digest the stuff about at least the Cauchy and Riemann integral definitions. I'd like to talk about that in some length. There are some variations on the definition of Riemann integral that make it interesting. There's two ways of defining the Riemann integral. It has to do with partitioning the real axis. One definition, the one that's repeated in the book here, you partition the interval over which you're going to do the integration. And you say the norm of the partition is the length of the largest subinterval that appears in the partition. So if the norm of the partition is forced to be small, that means you've really chopped it up into many, many pieces, small pieces. And if you take the limit of something that's based on the size of the partition, the norm of the partition, you might be able to find a sensible integral. That's one way you get the Riemann definition. You do your rectangle thing. You pick a so-called tag point inside each subinterval of the partition. A partition is just a set of points. It's chopping points along the axis between A and B. Rectangles go up at the chopping points, right? You pick a point, a tag point, inside each one of these subintervals, partition subintervals. Evaluate the function of the tag point. Multiply that by the width of the partition point. And add all that up. And watch, and you do that in principle, and you watch what happens to that grand total as the norm of the partition goes to zero. That is to say, the bases of all these rectangles are mutually forced to get smaller and smaller. If that approaches a limit, you say that the Riemann integral exists, and it is that value.
Now, when I was reading this, the question I had was, when you push the Cauchy integral Riemann, why is that second one necessary?
The Cauchy integral is the Riemann integral with the tag point always being the leftmost point.
But if the norm of the partition is 0,
Oh, yeah. Yeah, a Cauchy estimate, if the norm isn't small, can be wildly bigger than the actual area of the curve.
does the Cauchy take the limit of the norm?
Yes.
So it's something.
It's just that with the Cauchy definition, the tag point is always, I think, somewhere in the calc text. You remember you in chapter 5 of the calc book, you do a Riemann sum based on the left-hand endpoint, and then you do one based on the right-hand endpoint. Well, if you just stuck with the left-hand endpoint and let the partition shrink, the norm shrink, that would be the Cauchy. That would be the Cauchy integral. If you think of a function that is Riemann integral but not Cauchy integral, that's what I want to explore next week. There's some little technicalities that have to do with continuity. If something bad happens on one left end,
Oh, that's why Cauchy is strong.
yeah, it's not as strong. In fact, neither one of them is as strong as Tom Apostle's modification of Riemann. Apostle, I think he's still alive. He was a professor of mine. And you basically do this. You set up, instead of the norm of the partition, you pick an epsilon. They write it